Welcome to Spring LIB.
Okay, in this problem we have a water molecule composed of 2 hydrogens and 1 oxygen. Well, we are given the distance from the hydrogen to the oxygen. We're given the angle, the total angle, 104 degrees, that are formed between the 2 hydrogens. And we're given the dipole moment from the oxygen to the hydrogen, the total dipole moment, rather. We're first asked to find the effective charge on the hydrogen, and then we're asked to derive an expression for the electric potential that varies with theta and R. Okay, so to start, we're going to make extensive use of the fact that the dipole moment from the oxygen to one of the hydrogen molecules is identical to the other, at least in magnitude, and the angle from our axis of interest, which we will call the x-axis, the angle from that to the hydrogen is of 52 degrees. We're just cutting the total degrees in half. Another fact is that P1 is equal to Q times D, as with all dipole problems. So to start us out, we could say that the total dipole moment is equal to 2 times one of the dipole moments, P1, cosine of 52 degrees. Thus, P1 is simply P over 2 cosine 52 degrees, which is itself equal to QD. Thus, we can isolate Q. Q is P over 2D cosine 52 degrees. We can plug in our value for the total dipole moment and for the distance from oxygen to hydrogen, and of course cosine 52 degrees, and we will end up with about 5.2 times 10 to the negative 20 Coulomb. That's the effective charge seen by the hydrogen. Okay. Now, making use of the fact that P1 is equal to P2, which is equal to P over 2 cosine 52 degrees, we can begin to get the total potential, which is the sum of each individual potential due to a dipole field. The potential due to a dipole field is 1 over 4 pi epsilon naught P cosine over R, 2 degrees, minus our theta, R, P2. So this is really, this is P1, by the way. This is really a lesson, an exercise in geometry at the moment. So this is the sum of our potentials, which gives us our total potential. And at this point, once we're at this point, we're going to have to do a lot of math to get us down to the expected expression. We can pull the R out to start, leave us with something a little bit better. P2 degrees minus theta plus P2 cosine 52 degrees plus theta. Go into a new line. So at this point, we can use a trig identity to, well, not even a trig identity. We can simply express P1 and P2 in terms of the total dipole moment and pull it out of the larger expression. And then apply a trig identity. Cosine 52 degrees times cosine theta plus sine of 52 degrees times sine of theta plus cosine 52 degrees cosine theta, and of course one more term, sine of 52 degrees cosine theta. Okay, so that's complicated. This is just a generic trig identity. And then we can start collapsing things down and get us to the expected form. 1 over 4 pi epsilon naught r, p over 2 cosine 52, as usual. Simplifying what's in parentheses, we have 2 cosine 52 degrees times cosine theta. Get a little bit more cancellation to occur. And we have 1 over 4 pi epsilon naught p cosine theta over r, which is what we were looking for. It's a little bit tricky, some geometry and a little bit of trig substitution rules, but we got there. So that's it. Thanks.